Very good morning, students.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Good morning. Let us start with the discussion without wasting any time. Last class, we have been discussing about different concepts of optical activity. And then let us start with the optical isomers. So what are optical isomers? Like enantiomers. Optically active isomers, which are non-superimposable mirror images. Optically active isomers, which are non-superimposable mirror images of one another. They are said to be enantiomers. They have similar physical properties like melting point, boiling point, solubility, etc. and hence cannot be separated by fractional distillation. The enantiomers are non-superimposable mirror images. They have similar physical properties and thus they cannot be separated by fractional distillation. Configuration RS exactly opposite for enantiomers and symmetry is absent. If we have plane of symmetry and center of symmetry, obviously, if there is any symmetry element, then we can say because of the presence of symmetry element, one part of the molecule will be rotating by theta, means other part rotates by an angle same theta in the opposite direction. So that will lead to optical inactivity. Configuration RS exactly opposite for enantiomers and symmetry is absent. There is no plane of symmetry or center of symmetry. If one rotates a plane polarized light clockwise, the other will rotate anti-clockwise by the same amount. Like we have a particular compound A and that same compound I have taken in the mirror image. Yes or no? We'll take an example, you will get clarity. Like CH, Cl, Br, F, let us say. And its mirror image is going to be CH. Cl will be in this direction, F will be in this direction, Br will be in this direction. So these two are mirror images and they are non-superimposable with each other. So if one compound, let us say if it is rotating by an angle theta in the clockwise direction, other will rotate by the same angle theta in the anti-clockwise direction. If one compound rotates by an angle theta in the clockwise direction, the other will rotate by the same angle theta in the anti-clockwise direction. So net rotation, if you take equimolar, like 50% of this enantiomer and 50% of the other enantiomer, if you take, then the totally, if you try to add them, then you will be getting net rotation is going to be 0. So equimolar mixture of D and L forms is called racemic mixture and it is optically inactive due to external compensation. Meso compounds are optically active or optically inactive?
Optically inactive.
Due to what type of compensation?
Internal compensation.
Internal compensation, right? Very good. Equimolar mixture of D and L form is called racemic mixture and it is optically inactive due to external compensation. Separation of racemic mixture, like racemic mixture is two enantiomers, right? If you try to separate those two enantiomers, that is said to be resolution. So what is enantiomer? Enantiomers are non-superimposable mirror images. What is racemic mixture? Equimolar mixture of the two enantiomers, that is said to be racemic mixture. If we take equimolar mixture of two enantiomers, then obviously that will not have any net optical rotation. So that will also be optically inactive. This compensation is happening by one molecule to the other molecule. So it is said to be external compensation, not internal compensation. Right? What are these? COH, HCH3OH, COH, CH3, H and OH. What are these two compounds called as, students?
Enantiomers.
If I keep a plane mirror here, yes or no, you will be having CH3 reflected here, COH, OH and H. So these two are said to be non-superimposable mirror images. So they are said to be enantiomers. Okay. Enantiomers because non-superimposable mirror images. Try to keep a mirror here. COH reflected, COH reflected, H, OH, H and OH. So again they are non-superimposable mirror images. Enantiomers. Non-superimposable mirror images. Mirror images. They are called as your enantiomers. Non-superimposable mirror images, they are called as your enantiomers. So these compounds, whatever we have given in the first set and second set, they are said to be enantiomeric sets. Diastereomers, what are diastereomers? Can anyone define?
Non-superimposable, non-mirror images.
Non-superimposable, non-mirror images are said to be diastereomers. Like cis-trans isomers, they are also included in the diastereomeric set. Diastereomers may be optically active or optically inactive. Stereomers which are not mirror images of each other, we can say non-superimposable, non-mirror images, non-mirror images are called diastereomers. Non-superimposable, non-mirror images, they are said to be diastereomers. They have different physical and chemical properties. Like if you talk of enantiomers, enantiomers have different physical properties and chemical properties, or same physical properties. If you think of enantiomers, they have similarity in the physical properties, so they cannot be separated by fractional distillation. But if you look at diastereomers, they have the difference. Yes or no? So they have different physical and chemical properties, and hence can be separated by fractional distillation. They may or may not be optically active. They may be optically active, they may not be optically active. Generally, cis-trans isomers. Sorry. The cis-trans isomers, they are also called as diastereomers to each other. Example, you can take 1-butene. First example, you can take butene. That is, you can take in the cis form as well as in the trans form. So cis-butene as well as trans-butene, they are diastereomers to each other. They are cis-trans isomers, geometrical isomers, as well as diastereomers. Generally, cis-trans isomers are also diastereomers to each other because they are non-superimposable, non-mirror images. They are not mirror images, and they are not superimposable, so they are also called as diastereomers. Try to figure out these compounds. COH, CHOH, CHOH, are they mirror images to each other? If I keep a plane mirror here, so not mirror images, non-mirror images, so diastereomers. This is very, very important. This is what I have told you in the last class also. Sir, if Fisher reaction is given to you, then you can keep a plane mirror and then try to figure out whether they are enantiomers or not, diastereomers or not, and all. But if they have given Fisher reaction with changing the positions, like whatever the groups went on the right side, left side, their positions has been changed completely. Top, bottom positions changed. The top group is now present on the right side, bottom group left side, and left and right groups, they are on the top and bottom. In that case, whenever the positions of all the groups have been completely changed, the two compounds, it is go with the assigning of configuration. If compound A has R configuration, compound B has S configuration, and it has only one chiral carbon. If R configuration has been exactly converted to S, then they are said to be enantiomers because they are mirror images, right? Mirror images will be having the change in configuration. So if R configuration changes to S, then they are said to be enantiomers. This is a scenario when we have only one chiral carbon. When we have two chiral carbons, then you can have two chiral carbons, means you can use a configuration at both the carbons. We can say R and R at two carbons, let us say. If R and R is a configuration at two chiral carbons, then that configuration has to be changed to S and S. RR has to be changed to SS. That is, configuration at every chiral carbon has to be reversed. Then that is said to be enantiomers. If you have only one chiral carbon, and if that configuration has been reversed, then that can be your enantiomer. At every chiral carbon, if the configuration has been exactly reversed, then they are said to be enantiomers. RS converting into SR, they are also enantiomers, and if symmetry should not be there. If there is a presence of symmetry, obviously in that case, plane of symmetry present means optical inactive compounds. RR converted to RS, like two chiral carbons are there, two or more than two are there. Configuration at few carbons has been changed, and remaining all other carbons configuration is same. In that case, they are said to be diastereomers. Understood this point or not? This same logic when applied to 3D representation also, not only Fisher projection. Even though I have given 3D representation of a molecule to you, you can just find out the configuration. Configuration at every chiral carbon same in both the compounds means they are identical. Configuration at every chiral carbon is inverted or reversed means enantiomers. configuration at a few chiral carbons reversed and others are same means they are said to be diastereomers. Is that point clear?
Yes, sir.
Yes, sir.
Yes, right, very good.
Sir,
Yes, please.
sir, could you explain the third one of that enantiomers once more?
Here, this one,
Yes, sir. Yes, sir.
R and S, R changed to S, S changed to R. Configuration exactly reversed or not? Configuration is exactly reversed. Configuration exactly reversed means they are said to be enantiomers only. But there may be a possibility of symmetry because one compound has R, other compound has S. If all the groups are same, then symmetry may be present. If symmetry is present, plane of symmetry or center of symmetry, is it logical to call them as enantiomers?
No, sir.
No, that's what they mean to say. Like in case if you have RRSS, then there is no possibility of symmetry because at the second carbon also we have same type of groups, third carbon also same type of group means two chiral carbons, same configuration getting means you cannot have symmetry. If one is R, other is S, then there can be a possibility of symmetry. If symmetry is present, in that case, it is not going to be an enantiomer. RS, SR change happened, they are said to be enantiomers if symmetry is absent. Got it now?
Yes, sir. Thank you.
Yes. Meso compounds. What are meso compounds? Optically, yes, anyone? Meso compounds are optically inactive compounds which are optically inactive due to the presence of either plane of symmetry or center of symmetry. Yes or no? Meso compounds are optically inactive due to the presence of plane of symmetry or center of symmetry. Mirror image of meso compound is superimposable on it. So mirror image is identical to meso. The RS configuration of both chiral compounds of meso compounds is opposite. Due to internal compensation, meso is optically inactive. Ultimately, what we can say is plane of symmetry or center of symmetry is present. So one part of the molecule itself will be like if you take this part, this plane, it is symmetrical. This is a plane of symmetry. Plane of symmetry present means this part of the molecule, if it rotates in the clockwise direction theta, the other part rotates in the same angle but in the anti-clockwise direction theta. So net rotation would be 0. So meso compounds are those compounds which have more than one chiral carbon and are optically inactive due to the presence of either plane of symmetry or center of symmetry. Right? I have said you three types of questions. Which of the following are meso compounds? Which of the following are internal? Which of the following has internal compensation? Which of the following has plane of symmetry or center of symmetry? In all those three questions, we have to check the elements of symmetry only. Right? Try to look at this particular compound. So meso tartaric acid, two chiral centers are there. So we can just look at that particular plane of symmetry present. Because of the presence of plane of symmetry, one part if it rotates by an angle theta, other part will rotate by an angle theta in the anti-clockwise direction. So net rotation would be 0. So they are said to be meso compounds. Racemic mixture. Just now we have seen equimolar mixture of D and L enantiomers. That is said to be racemic mixture. If D rotates by an angle theta, the L compound will rotate by an angle same theta in the anti-clockwise direction. So net rotation would be 0. So net rotation 0 due to external compensation in racemic mixture. Net rotation 0 due to internal compensation in meso compounds. Racemic mixture is optically inactive due to external compensation. Why this all? Why we are all studying these concepts? You may ask a question. Because I will be explaining a reaction where racemization can happen. Can you think of SN1 reaction, all of you? Anyone remembered SN1? What is SN1 reaction?
Attacking of electrophile.
Yeah, what is the name, Faizan? SN1. Unimolecular nucleophilic substitution reaction. Yes or no?
Yes, sir.
Unimolecular nucleophilic substitution reaction. Initially, you look at the scenario, like we have a carbon, like I'll take an alkyl halide now, so that you can understand why you are studying all this. You can have CH3, 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 CCl bond, and you are treating this with a aqueous OH minus. In the presence of aqueous media, OH minus acts as a nucleophile or a base?
Nucleophile.
Nucleophile. In the presence of alcoholic media, OH minus acts as a base. So OH minus here acts as a nucleophile. And if you look at this carbon chlorine bond, if this bond cleaves, you will be generating what?
Tertiary.
Tertiary carbocation. So this is a tertiary alkyl halide which has a tendency to undergo the cleavage of carbon chlorine bond. Because of that cleavage of carbon chlorine bond, you will be generating what? Carbocation. So CH3, C, CH3, CH3. This carbon chlorine bond is slowly cleaved. Slowly ionization will occur to generate CH3, C, CH3, CH3 plus. This is the first step, step 1. Step 1 is the slow ionization to form a carbocation. Step 2, as the carbocation is formed, the rearrangements and ring expansions can occur if the carbocation is in such a way to gain stability. So the rearrangements and ring expansion are possible, or contractions are also possible. So that more stable carbocation is now going to be attacked. The most stable carbocation is now going to be attacked by the OH minus, which is acting as a nucleophile, and you will have this type of product. Understand this point carefully. Understand this point carefully. In the step 1, what happened? What is the hybridization of this particular carbon? Alkyl halide carbon. What is the hybridization of the carbon, which is the alkyl halide carbon? Hybridization, students.
sp3.
P3.
sp3 hybridized. What is the hybridization of this particular carbon?
sp2.
sp2. So now if I ask a question, what is the stereochemistry of the product? What is the stereochemistry of the product happening in this case? So you try to think on this question. I'll bring some pens so that you can actually visualize what is actually happening in the reaction. Okay, all of you try to think on what is the stereochemistry of this particular product uptake. I'll be back in just a minute. Yes, student, any ideas? Anyone?
Sir, both the sides are free to attack
Yeah.
the nucleophile.
Yeah, okay. So let us understand the same scenario. So Suman says the attack can be happening from both the sides. So imagine my wrist is the carbon atom now. It is the carbon chlorine bond, this particular pen. Okay. This particular is the carbon chlorine bond. The 3 other are same groups, that is methyl groups. Because that carbon is sp3 hybridized, I'll be having what scenario, students? Tetrahedral shape. Does it look like tetrahedron or not?
Yes, sir.
Yes,
Yes
sir.
or no? So this is my wrist is a carbon atom. To that carbon, chlorine is actually connected in the above fashion. And these 3 methyl groups are there. These 3 are methyl groups. First step, step 1, what happens? The carbon chlorine bond is going to be slowly cleaved. The carbon chlorine bond is slowly cleaved. The chloride is lost. As soon as the chloride is lost, this carbon gets what charge? Positive charge. So it becomes a carbocation now. As soon as the chlorine bond is weaved, as soon as the chlorine bond is leaved, you will generate a carbocation. Carbocation is having sp2 hybridization. sp2 means what? Trigonal planar. Though whatever the 3 groups are present in this fashion, they will now present in a single plane. Understood or not? They will now present in a single plane. Like there will be a plane passing through all these 3 groups in this fashion. In this fashion, they will lie in a single plane. Initially, they were tetrahedral carbon. Initially, there was a tetrahedral carbon. But in the step 1 of the reaction, what happened? In the first step of the reaction, the carbon chlorine bond has been leaved. So the groups which are present downward, they should be coming this direction to form a trigonal planar geometry. Now the geometry would be trigonal planar. Now you can think of OH minus as a nucleophile. The OH minus is a nucleophile. This is a nucleophile now. The carbon chlorine bond has lived. This marker pen is a nucleophile. So it can attack because it's a planarity is there, because it is a trigonal planar molecule. This carbon has positive charge. I can attack this OH minus from the top, or I can attack from the bottom. If I attack from the top, what happens? As soon as the attack is happening from the top, again this hybridization is what, students? What is the hybridization of this particular carbon? sp3 or not? sp3 means tetrahedral. sp2 means trigonal planar. Trigonal planar. As soon as the trigonal planar sp2 hybridized carbocation carbon that is attacked by the nucleophile, again we have a sp3 hybridization. So as soon as the OH minus attacks from the top, what happens? You will have again tetrahedral shape. Yes or no? Again you will be having
Yes.
a tetrahedral shape. But now the attack can also be from the top. I have attack from the top, but attack can also be from the bottom. If the attack is from the bottom, what happens? The T groups will be going in this fashion now, and you will have a tetrahedron like this. So this is also a tetrahedron. This is also a tetrahedron. This is a tetrahedron. This is also a tetrahedron. Just inversion happened or not? This is a tetrahedron where the leaving group was supposed to be in this fashion. The leaving group has been lost. The OH minus came and attack in the same direction. So we get again the same type of tetrahedron. Retention of the product happened. Same configuration. If the leaving group has been lost and the attack occurred from the bottom side, then you will have 3 methyl groups upwarted or inverted, and you will have nucleophile present in this direction. That means what happens in this particular course of reaction? You will be getting 2 enantiomers or not? Yes or no? Although we should not call enantiomers because 3 methyl groups are there. Let us take one is methyl, one methyl, one ethyl, and one propyl, or one methyl, one hydrogen, and one ethyl. I can take like that because I want to just maintain a chiral carbon. Hydrogen C2H5, hydrogen C2H5, hydrogen C2H5. So what actually happened here, students? The attack happened from the front side as well as from the back side. Which one is more feasible? What, according to you, which one is more feasible? From the front side or from the back side? Or both can happen?
Sir, backside is slightly more feasible.
Yes, very good. Back side is slightly more feasible when compared to front side, because although we said the carbon chlorine bond has been lost, that chloride ion is in the reaction mixture, it is not taken out from the reaction mixture. The diffusion of chloride ion is slow. Understand this point carefully. Although we are saying carbon chlorine bond is cleaved, the Cl minus is lost. Lost means what? In this particular reaction mixture, I am doing the reaction. Here we have an alkyl halide. Carbon chlorine bond is lost means it is still present in the solution only. I am not taking the chloride ion out of this mixture. Understood that point or not? The chloride ion is lost. The chloride ion which is present in the reaction mixture, that has to interface or interact with the adjacent solvent molecules. The Cl minus has to interact with the adjacent solvent molecules. So Cl minus has to undergo collisions. So it cannot be moving out separately or very far away from the carbocation. So its concentration was still present somewhere near. So what happens in this case is, so the attack of nucleophile in SN1 can occur from back side as well as front side, but back side attack is slightly feasible. You can think like if you just have a carbocation, the attack from the bottom as well as attack from the top is same. But in reality, backside attack is slightly more, as the Cl minus ion didn't diffuse greatly, did not diffuse greatly. So we'll have what type of stereochemistry we'll have? So racemization occurred or partial racemization occurred? So partial racemization occurred. If we have exactly 50% D and 50% L, 50% front attack and 50% back attack, then raceme mixture. But here completely 100% racemization did not occur because backside attack is slightly high. Like we can say 70% back attack and 20% or 30% front attack. In that case, you can say partial decimation is going to happen. So that is what actually this importance of this concept. So using knowing racemic mixture and all, you can understand or predict what happens in the stereochemistry as the reaction has been changed or as the reaction has been done, right? So this is just an example, simple example. After GOC, we look at all the reactions as well, different types of reactions, addition reactions, elimination, substitution. All those cases we will study. Right, students? Find relationship between following compounds. I have given two compounds to you. What is the relationship between them? MECHOHCl, MECH CClHOH. Here, if you look at F, hydrogen and chlorine, hydrogen was top, chlorine was bottom. But here chlorine was top, hydrogen was bottom. So can I just reverse this molecule? Can I rotate this molecule by 180 degree? Rotate by 180 degree. If I rotate by 180 degree, I'll be getting this scenario. Chlorine will be here. If I rotate by 180 degree, chlorine will be above, hydrogen will be down, OH will be here, methyl will be here. Now compare what are these? Chlorine above, hydrogen below. If I keep mirror images, these two are mirror images. Enantiomers. Non-superimposable mirror images, that's said to be enantiomers. Got it or not?
Yes, sir.
Because
Yes,
I have
sir.
like hydrogen and chlorine positions, hydrogen is top here, chlorine is bottom. I have made the chlorine go to top and hydrogen made to bottom. So I have rotated by 180 degree. And we all know rotation by 180 degree do not change the stereochemistry or the configuration. So in this case, I am getting methyl on the right side, OH on the left side. Methyl is on the left side, OH on the right side. So if I try to compare, these two are non-superimposable mirror images, nothing but enantiomers. And one more thing you can do. Here I have given the Fisher projection. So directly you have written in this fashion, done the interchanges and performed like non-superimposable mirror images. Other thing what you can do is finding out configurations. What is the configuration here? First atom is chlorine connected directly to the carbon, which has more atomic number. So first priority, second priority, third priority, 1, 2, 2, 2, 2, 3. How we are going in the anti-clockwise direction? Anti-clockwise means S. Clockwise means R, anti-clockwise means S. And since the fourth priority is already on the vertical line, I have not changed that configuration. MECClCHCOH. First priority will be given to chlorine. Second priority to OH. Third priority to methyl. 1, 2, 2, 2, 2, 3. How we are going? In the clockwise direction. Clockwise means R. So S configuration changed to R configuration. Configuration exactly reversed. Only one chiral carbon, S has been changed to R. So what is the relationship between these two compounds? They are said to be enantiomers. Like that, whenever two compounds has been given to you, and if you can't do the rotations or interchanges, find the configuration. If configuration is exactly reversed, they are said to be enantiomers. Try to do second question. Find the relationship between the following compounds. Now they have given 3D representations. Whenever they have given 3D representation, again you have to do the same logic. Assign the configuration, R and S nomenclature. So lowest priority group has on the dash line. So in the second compound, lowest priority group is fourth. That is hydrogen, fourth priority group. That is on the dash line. So give the priority. OH will be having first. Ethyl will be second. Methyl will be third. 1, 2, 2, 2, 2, 3. How we are going in the clockwise? So it is having R. Here OH is not there on the dash line. So what you have to do? You have to perform even number of interchanges. So I'll interchange hydrogen and OH. I'll interchange methyl and ethyl. So what happens now? Ethyl will be going here. Methyl comes to this position. OH will be here. H will be here. Fourth priority hydrogen on the dash line. So give the numbering now. 1, 2, 3. How we are moving? 1, 2, 2, 2, 2, 3. In the clockwise or in the anti-clockwise direction? Anti-clockwise. Anti-clockwise means
S
yes. So R and S. So what are they? Enantiomers. One compound has R configuration, other has S. So obviously the configuration has been exactly reversed. So one chiral carbon configuration exactly reversed means enantiomer. If we have more than one chiral carbon, configuration at all the chiral carbons has to be exactly reversed. So these are said to be enantiomers. Find relationship between the following compounds: COH, CHOH, COH, CH3, COH, and COH, CCH3OH, COH, COH. What are these? Find relationship between following compounds. These are the two compounds given to you. What is the relation between them? What you have to do? Just to figure out the configuration. Yes or no? And if you think logically, COOH is connected to carbon, carbon connected to OH and H. COH is connected to carbon, carbon connected to CH3 and OH. That means this carbon and this carbon are same or different. This carbon is connected to H and OH. This carbon is connected to CH3 and OH. So actually this carbon and this carbon are same. So I want to rotate this molecule by 180 degree. I will try to rotate by 180 degree. What happens in that case? Bottom and top, since they are both COH will be here. Rotated by 180 degree, what happens? CH3 will be here now. Rotation by 180 degree. CH3 will be here. CH3 will be here or here. To this particular position, right? Yeah. OH will be on the right side. What about other? This OH will be on the left side. This hydrogen will be on the right side. What are these two compounds? This compound and this compound.
Identical.
Same, right? CH3OH, COH, COH. They are going to be identical. Okay. And you should not say like, sir, here I'm getting R configuration, here I'm getting S configuration. No, because this carbon is different, this carbon is different. These two carbons are same. These two carbons are different carbons. Okay, different carbons, because look at the connectivity. What are these two compounds? Find relationship between these two compounds. First one and second one. First one looks like cis or trans. Are they cis and trans isomers? Yes or no? Because if you look at the double bond here, the two methyl groups of the CH2 connectivity is on the same side, so that is going to be cis. Whereas in the first two compounds, they are on the opposite side, so that is said to be trans. Cis trans isomers, they are also called as diastereomers. So what is the relationship between these two compounds? They are geometrical isomers, that is cis trans, as well as diastereomers. Geometrical isomers and diastereomers. Find the relationship between these two following compounds. CHO, OH, COH, OH, CHO, COH. You can do interchanges and then look at non-superimposable mirror images or not. You can also give the priority order. Oxygen gets the first priority, second priority C double bond OH, C double bond OH. C double bond OH will get the second priority, CHO third priority. 1 to 2, 2 to 3. How we are going? Clockwise direction. Clockwise and fourth priority group on the horizontal line. So it should be S. What about this? First priority, second priority, third priority. 1 to 2, 2 to 3 are going in the anti-clockwise direction. Fourth priority in the horizontal line. So it should be R. So S and R, what are they?
Enantiomer.
Enantiomers. Okay. So directly you can just go with the configuration checking. Assign the configuration. S and R you can assign. So configuration has been exactly opposite. So they are directly said to be enantiomers. What are these? Find the relationship between the following compounds 1, 2, 3, 4. 1 and 2, 1 and 4 or 2 and 4, 1 and 3 or 2 and 3 or 3 and 4. All of you try to solve it. Same, you assign the configuration, that's it. Configuration you try to assign at every carbon atom. Configuration you try to assign at every carbon atom, then you will be getting an idea whether they are R and S or S and R or what are they, like enantiomers or diastereomers. First compound, what type of configuration you are getting? First compound. So this is a carbon to which SH is connected. To this particular carbon, what is the R or S? The second position, third position. So SH will be having the highest priority 1. First priority will be here. Second priority here. Third priority here. 1 to 2 to 3. you're going the clockwise, so it should be R, but fourth priority is on the horizontal line, so it should be S, 2S, 2S comma, then why I'm saying 2S, because I have to give the numbering like this, 1, 2, 3, 4. So second carbon you have S configuration, third carbon you have 1, 2, 3, anti-clockwise direction, so R, 2S comma 3R. Second compound 1, 2, 3, anti-clockwise direction, anti-clockwise means S, because hydrogen is already in the vertical line, so 2S comma, next 1, 2, 3, first priority, second priority, third priority, clockwise direction, clockwise means R, 2S comma 3R. Third, first priority, second priority, third priority, anti-clockwise direction means S, but it should be R, so 2R comma, first priority, second priority, third priority, anti-clockwise means yes, but it should be R because fourth priority is on the horizontal line, 2R comma 3R. Fourth group, first priority, second priority, third priority, clockwise direction, R, so directly R because hydrogen is on the vertical line, fourth priority, so 2R comma, first priority, second priority, third priority, you are going in the clockwise, and hydrogen is on the fourth priority, so 2R comma 3S. Try to figure out now what are 1 and 2. 1 and 2 are what?
Identical.
Identical. And 1 and 4 and 2 and 4, what are the 1 and 4? 2S 3R converted to 2R 3S. 2 and 4, 2S 3R converted to 2R 3S. What are 1 and 2 and 2 and 4?
Diastereomer and enantiomer.
Diastereomers or enantiomers?
Enantiomer.
2 and 4 and
Enantiomers. What about 1, 3? 1 and 3 means configuration at 1 carbon changed. 2S changed to what? Yeah, 2 and 3 again same. 3 and 4 again same. So they are said to be diastereomers. So like that, you have to assign the configuration. So what are the compounds given to you, whether they are enantiomers or diastereomers? This is how you have to assign. So 1 and 2 are identical. 1 and 4, 2 and 4 are enantiomers. 1 and 3, 3 and 2, 3 and 4, 2 and 3 are diastereomers. Everyone got this or not?
Yes,
These
sir.
are famous questions. Most of the students gets confused. That is why assign the configuration RS nomenclature properly. Try to figure it out whether R or S at every chiral carbon. Check out the correct relationship between the type of compounds given to you. Right? So A is homomers are identical. Homomers is also means identical. B means enantiomers. 1 and C is diastereomers. We got the same. So that is what about your different types of relationship between different types of compounds. Optical activity, compounds having no chiral center but may be optically active. What are the examples I have given here?
Allenes.
Allenes and
Biphenyls.
biphenyls. Very good.
Biphenyls.
First one is allenes. Substitute allenes or cumulines. They are going to be optically active in nature. So understand this carefully. C double bond, C double bond, C. Like whenever we have even number of double bonds, whenever we have even number of double bonds and the configuration on the first carbon and the third carbon, they are going to be exactly perpendicular to each other. Understand this point. Whenever we have even number of double bonds, the terminal carbon atoms, they will be having valencies which are perpendicular to each other. Whenever we have odd number of double bonds, there you will be having the valencies on the terminal carbon atom on the same plane. So whenever you have even number of double bonds, you can look at optical activity, and you should not have same groups connected to the terminal carbon atoms. Same like geometrical isomerism. If to the carbon-carbon double bond, if one of the carbon contains two same groups, it is not showing geometrical isomerism. Same way, C double bond, C double bond, C. If one of the terminal carbon has two same groups, then it will not be optically active. Two conditions you have to check for optical activity. First, you should have even number of carbon atoms. Second condition, the terminal carbon atoms. Each terminal carbon atom should be connected with two different groups, not the same groups. Okay, even number of double bonds should be there. And you should have terminal group not present in the same plane. Terminal groups are not present in the same plane whenever we have n number of double bonds. Each sp2 carbon have two different groups, then optically active because there won't be any plane of symmetry or center of symmetry. So is this compound optically active given to you? How many double bonds are there? 1, 2, 2 double bonds, even number of double bonds. Whenever you have even number of double bonds, then only the valencies of the terminal carbons, they will be perpendicular. That means this carbon has CH3 and H on the plane, means to the other terminal carbon you have CH3 and H, one above the plane and the other below the plane. So even number of double bonds are there and no carbon has two same groups, so it is optically active. Optically active. Whenever we have odd number of double bonds, 1, 2, 3, 3 double bonds are there, then the valencies of the terminal carbon, they are in the same plane. So this CH3, this hydrogen, this CH3, this hydrogen, they are in the same plane. So always there is a plane of symmetry present. If a plane of symmetry always present, they are optically inactive. Okay. Odd number of double bonds. Odd number of double bonds means terminal group present in the same plane. If terminal group present in the same plane, always contains plane of symmetry, that is the plane in which the molecule contains. Always contain plane of symmetry, so it is going to be optically inactive. It is going to be optically inactive. Let us now look at examples, you'll get clarity. This is how the molecule is. C double bond, C double bond, C. You look at the molecule. This particular terminal carbons, if one carbon has the groups in the plane, the other carbon groups will be perpendicular, like outside the plane, one above, one below. Which of the following compound is optically active? Like this compound has been given to you, is it optically active or inactive?
Active.
Number of double bonds. How many double bonds are there? Two double bonds are there. And each carbon, each terminal carbon is connected to different groups, so optically active. Okay, number of double bonds is 2, even number of double bonds. And no plane of symmetry or no center of symmetry, as different groups were connected, were present to each sp2 hybridized carbon. So optically active. Is it optically active or inactive?
Optically inactive.
Inactive.
Even number of double bonds are there, but two methyls are same, so it is going to be inactive in nature. Contains plane of symmetry. Plane of symmetry present. Number of double bonds are even. That's not the ultimate condition. You should have two different groups connected to the terminal carbon. Terminal carbons have same group, so plane of symmetry would be present. So optically inactive. What about third case? CH3, CH, C double bond, C double bond, C double bond, CH3H. Number of double bonds how many? 1, 2, 3. 3 double bonds are there. Odd number of double bonds are there. Means directly the
Optically
molecular
inactive.
plane. Yes or no? Plane of symmetry is present. Plane of symmetry present, so inactive. Optically inactive since plane of symmetry is present. Number of double bonds 3 means obviously plane of symmetry is present, so optically inactive. No need to check any other thing. Which of the following compounds is optically active? CH3, C, C2H5, C double bond, C double bond, C double bond, C, ClCl. Both chlorines are same, and also we have odd number of double bonds. So there is no possibility plane of symmetry is present, so inactive. Number of double bonds 3, plane of symmetry present, so optically inactive. So not only this 2 double bond, 3 double bond, even if I have this system C double bond, 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 C, 1, 2, 3, 4 double bonds, CH3H, HCH3. Is it optically active or inactive?
Optically active.
Active. So you should not worry about the number of double bonds, and I don't need to mention always this H and CH3 above the plane and below the plane. You have to get an idea. Like these hydrogen and CH3, if they are on the plane, this methyl and hydrogen, they should be one above and the other below. So it is optically active because even number of double bonds are there. So terminal carbons has perpendicular valencies. Right? Next, consider the biphenyl system. Biphenyl means this type of system where two phenyl groups are connected. Two phenyl groups are connected in this fashion. So rotation around carbon-carbon single bond is accepted or not accepted, students? Rotation around carbon-carbon single bond, that is accepted. Free rotation is possible. So free rotation possible means plane of symmetry present or not? Look at the biphenyl. One biphenyl is present in this fashion, like one hand. Other biphenyl, other hand like this. They have a carbon-carbon single bond. So these two are connected by single bond. So free rotation is possible. I can rotate one phenyl group with respect to other phenyl group. So if you consider a plane which is containing both the phenyl group, that is a plane of symmetry. So plane of symmetry is present. In the case of plane of symmetry, in the presence of plane of symmetry, optical activity is not present, so optically inactive. So that is the two phenyl groups, and the plane is actually considering the two phenyl groups. Like you can have a paper like this. Like with respect to the paper only, I have two phenyls. Yes or no? In the same paper itself, I have two phenyl groups present. So since two phenyl groups are present in the same plane, so plane of symmetry is present. If there is a plane of symmetry, optical activity is not present. So optically inactive nature. Right? Is that point clear or not?
Yes, sir.
Now what happens whenever we have a substitution at all the ortho positions? Understand this point carefully. So that is how your biphenyl system is actually looking like for your animation, but you have to visualize all this. The animations are not available in the exam, right? You have to visualize, think of how the molecule actually is there. Animations are good only for one moment of time to understand, to visualize, but you have to keep all that in your mind. So how the molecule is actually in reality. Ortho substituted biphenyls. If all the four ortho positions are occupied by bulky groups, then to minimize repulsions, the rings become perpendicular to each other. Now you have the system like this. The biphenyls are there with respect to this phenyl. This is ortho positions substituted by A dash. With respect to this phenyl, these are also ortho substituted by B dash. So bulky groups are R, Cl, Br, iodine, CHO, COH, COR, CONH2, SO3H, NH2. Yes or no? These are the bulky groups. These are the bulky groups. Whenever you have a bulky groups, what will happen? Try to understand this point carefully. This here have A, here we have A dash, here we have B, here we have B dash. Generally, rotation is happening, free rotation with respect to one phenyl group, other phenyl group has to rotate. But here somewhere we have ortho position, that means somewhere we have a group like this. This is one phenyl, but the ortho position is substitute like this. Somewhere here also we have a group like this. Yes or no? This is another phenyl. Here also in this phenyl also we have groups. Now I am trying to rotate this carbon-carbon bond. This carbon-carbon bond, whenever it is rotating, whenever this phenyl group is in this plane, and whenever the other phenyl goes perpendicular, in that way, in that particular position, when the two phenyls are actually perpendicular, the repulsions between the ortho substitutions are going to be minimum. Understand this point. We are saying free rotation is possible, but whenever all the ortho positions are actually substituted, in that substitution case, what happens? With respect to one phenyl group, the other phenyl group will become perpendicular. If one phenyl group is present in this particular plane, if one phenyl group is present like this, the other phenyl will be like this. If one phenyl is in this particular paper plane, the other phenyl will be in this paper plane. Understood that point, students? Okay. Horizontal plane, and this will be in the vertical plane. Understand this point carefully. This phenyl group, if it is in the horizontal plane, the other phenyl group will be in the vertical plane. Why? Because to minimize repulsion between the ortho substituted compounds. This is how the planes are. One phenyl will be in the horizontal plane, means other phenyl will be in the vertical plane. Are you getting the scenario how the phenyls arrange themselves? The phenyls, although they have free rotation accepted around carbon-carbon single bond, but they are not allowed to rotate because of repulsions, and they arrange in the minimum repulsion direction in this way. So no plane of symmetry or center of symmetry present or not. Here is there a plane of symmetry or center of symmetry? Whenever we have, like you consider any plane, there is no symmetry. Whenever all the ortho positions have been substituted, there is no point of plane of symmetry or center of symmetry, so they can be optically active. Under what condition? Under what condition? The two groups present on the ortho position, they have to be different. On either on this phenyl or the other phenyl, if you have NO2 here and NO2 here, then plane of symmetry would be there. Yes or no? If we have two same groups at the two same on the same phenyl at the two different ortho positions, then you will be having a plane of symmetry. Again, the condition. Write down the condition. This molecule is optically active or inactive? CH3, CH3. You can directly say now. NO2, CH3. Okay. The biphenyls, the ortho substituted biphenyls are optically active when there is no plane of symmetry. There is no plane of symmetry in either phenyl rings, in both phenyl rings. In both phenyl rings. If both the phenyl rings do not have plane of symmetry, then under that condition, what you can say is there is a no plane of symmetry, means there is a possibility of optical activity, and thus they are said to be optically active in nature. So is this compound optically active or inactive?
Optically active.
Plane of symmetry is present if you look carefully, because with respect to this phenyl, I have CH3 and CH3 exactly on the same ortho positions. Plane of symmetry present means optically inactive. Active or inactive? Plane of symmetry present means inactive. Yes or no? Optically inactive. Look at this compound. Optically active or inactive?
Inactive.
So if you look carefully, we have NO2 and CH3 different. But if you look at this biphenyl system, both the iodines are same at the ortho positions, but they are not symmetry. Although iodines are same, here meta substitution methyl is there. If you consider any plane, that is not symmetry. So no plane of symmetry. Optically active. Optically active. Like that, you have to look at the optical activity in allyne systems and biphenyl systems. Similar type of alkylidine systems also there. You have to apply the same logic. Terminal carbons should be having different groups. Same groups, that means optically inactive.
Sir,
Yes, please.
in first one you said no, sir. Plane of symmetry, how it will exit, sir?
In which one? This one.
Yes, sir.
So look at that compound. How the compound should be. One should be in this plane. Like these are the two planes, two papers. If you consider, see, one phenyl will be in this plane, other phenyl will be in this plane. Yes or no?
Sir.
One phenyl will be in this plane, like horizontal plane, other phenyl will be in the vertical plane. You consider the phenyl in the, like this left side phenyl you consider. Let us say this is in the vertical plane. With respect to that phenyl, on the ortho position, you have methyl group above, you have methyl group below. So with respect to this horizontal plane, if I am considering this vertical plane, and with respect to this horizontal plane is exactly dividing the molecule in two halves or not? Because if I am dividing this, above I am having CH3, below also I am having CH3 at the ortho positions. Are you getting this logic?
Yes, sir.
See, this is how this animation, is it clear or not? This animation, you look at this animation. These two phenyls are perpendicular to each other. This is one phenyl, this is other phenyl. Here I have CH3, here also I have CH3. Then this plane is symmetrical or not? This is a plane of symmetry. These two phenyls are perpendicular with respect to one phenyl at the two positions, ortho positions. If you have same groups, then whatever the plane I am considering, that is nothing but your plane of symmetry. Because the above group is C connected to CH3, CH2. Below also we have carbon connected to CH3 and CH2. Both are same. But here symmetry is not there. Got it or not? If you still have doubt, what you can do? Shortcut. You consider one phenyl at one time separately. If you consider this particular total biphenyl as this particular system, this is CH3, this is CH3, and the other biphenyl like this, NO2, CH3. You consider in this particular biphenyl there should not be any plane of symmetry. If I consider plane like this, is it symmetry or not?
Sir.
Symmetrical plane is there, so it is a plane of symmetry. So what I have said, the ortho substituted biphenyls are optically active when there is no plane of symmetry in both phenyl rings. If I consider this phenyl ring, there is a plane of symmetry present, so it is going to be optically inactive. Second molecule also you consider the same way. Two phenyls you consider separately. One phenyl in this fashion, NO2 CH3, other phenyl in this fashion, iodine CH3. If I consider like this plane, so it is not symmetrical because one side I have iodine, other side I have iodine CH3. If I consider plane like this, one side I have NO2, other side is methyl. So both the phenyls are not having plane of symmetry, and in both the phenyl systems, ortho substitutions are there. So it is going to be optically active, no plane of symmetry and all. Clear now?
Okay, sir. Thank you, sir.
Okay, fine. If you have any difficulty finding the planes considering the biphenyl system at a time, you consider both the phenyls separately and check for plane of symmetries. No phenyl should have a plane of symmetry. Right. Calculation of total number of optical isomers. This formula are important. You have to just remember this formula. Unsymmetrical molecule. If the molecule is unsymmetrical in nature, then optically active isomers are 2 power n. Number of meso are 0. Total optical isomers is optically active isomers plus meso compounds, that is 2 power n. Symmetrical molecule. If the molecule is unsymmetrical, 2 power n, 0 and 2 power n. If the molecule is symmetrical, and we can have even number of chiral centers or optical centers and also odd number of chiral center or optical center, then the number of optical active isomers is 2 power n minus 1 minus 2 power p minus 1. Whenever we have odd number, p is equals to n plus 1. Whenever we have even number, p is equal to n by 2. So 2 power n minus 1 minus 2 power p minus 1. 2 power p minus 1 will be the number of meso. Total number will be number of optically active plus number of meso. That is 2 power n minus 1 minus 2 power p minus 1 plus 2 power p minus 1. Ultimately become 2 power n minus 1. Ultimately becomes 2 power n minus 1. When n is equals to even, in that case p is equal to n by 2. So number of optical active is 2 power n minus 1. Number of meso is 2 power p minus 1. And the total number of optical isomer will be like optical active isomer plus meso compound. If you try to add 2 power n minus 1 plus 2 power p minus 1. Everyone got this or not?
Yes, sir.
So this formula we will apply now to different sets of molecules: CH3, CHOH, CHCl, CHBr, CH3. Try to figure out now. Number of optical active isomers how many? Number of meso how many? Number of optical isomers how many? Number of resin mixture how many? Is it molecule symmetrical or unsymmetrical? Look at the molecule. Is that symmetrical or unsymmetrical?
Unsymmetrical.
CH3, CHOH, CHCl, CHBr, CH3. It is going to be unsymmetrical. Unsymmetrical molecule. Number of optical active isomer will be how much? 2 power n. Number of meso will be 0. Number of optical isomers total, that is active plus meso, 2 power n plus 0, that is 2 power n. Number of resin mixture will be half of number of optical active. So let us write the solution. So how many, what is n value here, students? What is n? N is equals to, n is nothing but number of chiral centers. How many chiral centers are there? 3 chiral centers. So n is equal to 3. So number of optical active isomers will be 2 power 3, that will be is equal to 8. Number of meso is 0. Number of optical isomers is 8 plus 0, that is equals to 8. Number of resin mixture is going to be 4. Yes or no? That is half of optical active isomers. Half of optical active isomers, that is 4 resin mixtures you are getting. Is that clear or not?
Yes,
Just,
sir.
just based on formula, we have to apply this.
Yes, sir.
Try to solve next question. CH3, CHOH, CHOH, CH3, symmetrical or unsymmetrical?
Symmetrical.
Symmetrical. Symmetrical case, number
Symmetrical.
of double bonds, that is number of optical centers or chiral centers. How many? 2 chiral centers. So
2.
even number of chiral centers. So what is the formula? Number of optical active isomers, 2 power n minus 1. Number of
N
meso,
minus 1.
2 power p minus 1. 2 power p minus 1 is p is what? P is equals to n by 2. So number of optical active is 2 power n minus 1, that is 2 power 2 minus 1, that is 2. Number of meso compounds will be 2 power p minus 1. P is n by 2, so p is equal to 2 by 2, that is 1. So 2 power p minus 1 is 2 power 1 minus 1. 2 power 0, anything power 0 is 1. Number of meso is 1. Number of optical isomers. Number of optical will be number of optical active isomers plus number of meso, that is 2 plus 1, that will be 3. And number of residue mixture,
1.
half of number of optically active, that is half of number of optically active isomers. That will be half of 2, that will be 1. Got it now, everyone? Should not get confused here.
Yes.
Okay. Then calculation of total number of stereoisomers. Total stereoisomers, how to calculate? If a molecule is unsymmetrical, total stereoisomers will be 2 power n directly. What is n? Number of geometrical isomerism center plus number of optical isomeric center. If the molecule given to you is unsymmetrical, then total number of stereoisomers is given by number of geometrical isomerism center plus number of optical isomerism center. In case of ring system, where geometrical isomerism center and optical isomerism center same, then number of stereoisomers is equal to number of optical isomers. Understand this point? In case of ring system, also for cycloalkanes also geometrical isomers are possible. Under what condition geometrical isomerism is possible for cycloalkane? We should have at least 2 sp3 hybridized carbons with different groups connected. In case of ring system, where geometrical isomerism center and optical isomerism center are same, then number of stereoisomers is equal to number of optical isomers only. So stereoisomers is equal to optical isomers. Try to solve this example. Find the total number of stereoisomers of the following compounds. Is this compound? Check out this. Here we have methyl, here we have hydrogen, here we have methyl, here we have hydrogen. We can also have this scenario. We have hydrogen methyl, we have hydrogen methyl. So these are nothing but cis and trans or not? This is trans. If you look for geometrical isomers. And for the same compound, here we have methyl, here we have methyl. Can I call this as chiral center? Because to this particular carbon, one side we have methyl, other hydrogen, other we have CH2, this side I have CHMe. So this is a chiral center. Can I call this also as a chiral center?
Yes, sir.
So it is a cyclic system. It is a cyclic system. This formula, it belongs to this formula. In case of cyclic system, where geometrical isomerism center and optical isomerism center, they are same. That means with respect to these two centers only, we have geometrical isomerism. With respect to these two centers only, we have optical activity. So when in case of ring system, when GI center, geometrical isomerism center and optical isomerism center same, then total number of stereoisomers is equal to number of number of optical isomers. Number of optical isomers. How to calculate number of optical isomers for this case? How many number of, is it symmetrical or unsymmetrical, this molecule? It is symmetrical, and you can have how many number of double bonds, how many number of optical centers? N is equal to 2. So total stereoisomers is equal to total optical isomers. What is the formula, students? Total optical isomers formula. Stereoisomers is equals to optical isomers, that is equals to, it is a symmetrical molecule where the number of double bonds is where the number of optical centers or chiral centers is even. So number of optical active is 2 power n minus 1. Number of meso is 2 power p minus 1. What is p? P is equal to n by 2. So total will be is equal to 2 power n minus 1 plus 2 power n by 2 minus 1, that is p minus 1. Substitute now. Here n is equal to 2. So total stereoisomer will be 2 power n minus 1. What is n? N is actually
2.
2. So 2 power 2 minus 1, that is 2 power 1 plus 2 power 0. 2 power 1 is 2, 2 power 0 is 1. So total stereoisomers will be 3. Got it now?
Yes.
Everyone got this or not? So this is how you can actually,
Sir,
yes please.
sir, in this molecule is plane of symmetry present?
So the Faizan, we are just doing by the molecular formulas and all. We can actually go with logics also. So this molecule is given to you. This molecule exists in these two forms. Yes or no? Cis form and trans form. In the cis form, plane
Yes.
of symmetry is present or not?
Yes, sir.
Plane of symmetry present. So cis molecule is only one molecule. In the trans form, plane of symmetry is not present. So it will be giving two isomers. So 1 plus 2, that is 3. We got 3 only.
Okay, sir.
Okay. In the cis form, there
Yes.
is a plane of symmetry. So it is only one isomer. In the transform, plane of symmetry is absent. So we can have D and L. So 1 plus 2, that will be total 3. This you can do
Yes.
whenever the ring is small. This you can do whenever I give a cyclopropane to you. Whenever I give a very large ring where you have more number of chiral centers, then you have to apply this formula, then do the calculation with respect to the formula. Okay.
Okay, sir.
Okay, right. So total number of stereoisomers of the following compound: CH3, CH double bond CH, CH3, CH2, CH3. Symmetrical or unsymmetrical?
Unsymmetrical.
Unsymmetrical. How many geometrical centers are there? One geometrical center. This is geometrical center. CH double bond CH. This is geometrical center. Geometrical center. This is optical center.
Opticals.
So n is how much? N is equal to 2.
2.
N is equal to means what is the number of stereoisomers? 2 power 2. That will be 4. Stereoisomers will go 2 power n because unsymmetrical, and number of geometrical isomers plus number of optical centers, that will be is equals to 2. So you can simply write total number of stereoisomers will be 4. Like we can apply the same logics logically again. We can have CH3, CH double bond CH, CH, CH3, CH2, CH3. Here I can have D form and here I can have cis. D form trans. And also I can have L form cis. And also I can have L form trans. So how many are there in total? Like this chiral center I can have D configuration and I can have cis here. At this chiral center I can have D configuration like a D optical rotation and I can have trans. At this particular chiral center I can have L rotation and I can have cis, L and trans. So you have 4. So that is nothing but total number of stereoisomers is 4. Just unsymmetrical molecule means 2 power n direct formula. Find total number of stereoisomers of the following compounds: CH3, CHOH, CH, CH3, CH double bond CH3. CH double bond CH3, it is nothing but geometrical center. Geometrical center. It is optical center. It is also optical center because chiral carbons. So n is how much? N is equal to 3.
3.
Total number of stereoisomers will be 2 power 3, that will be 8. Total number of stereoisomers will be 2 power 3, that will be is equals to 8. Everyone got it or not?
Yes, sir.
Yes, right. Very good. These are the questions where people get confused. That's why I'm giving a lot of examples. Total number of stereoisomers of the following compound. Try to figure it out. CH3, CH double bond CH double bond CH, CHCl, CH3. Try to solve it now. Total number of stereoisomers. How many?
8.
Varshita says 8. What about others? Manashi says 16. Any other options? So here we have CH3, CH11C, 11CH. What is this? How many number of geometrical centers are there?
2.
So we should not consider C11C as a geometrical center. It is an alien system or not? It is an optical center.
Yes, sir.
It is an alien system is alien system. So optical center. And you have here one more optical center. So n is equals to 2. 2 optical centers are there. There is no geometrical center. So 2 power n, that will be giving 4. So stereoisomers, total number of stereoisomers will be 2 power n, because unsymmetrical molecule, number of optical centers plus number of geometrical centers, that is just a 2. So you will have n is equals to 2. So total number of stereoisomers will be 4. That means what you are going to have is C11C. With respect to that, we have CH3 here and H here. With respect to that, we have CH3 here and Cl here. So with respect to this, I can have D and L. D and L. With respect to here also, I can have D and L. So DD, LD, and I can have DL, LL. Yes or no? So here I can have D, optical rotation. Other side also I can have D. L and D, D and L, L and L. So total number of stereoisomers will be 4. The total number of stereoisomers will be 4 in this particular case as well. Then comes the last concept in optical isomerism, like amine flipping. I have told you about this amine flipping in the last class also. Whenever we have one chiral carbon, it is directly optically active, except a few cases. What are those few cases? Ring flipping occurs or amine flipping occurs. So let us look at that. So nitrogen having methyl group, ethyl group, and hydrogen connected, it is a secondary amine, and nitrogen also has a lone pair of electron. It has one chiral center but optically inactive. Why? Whenever we have one chiral centers, it should be optically active, but here it is optically inactive. Why? Means in open chain amines in which lone pair of nitrogen present in sp3 orbital, amine inversion takes place. That means the rapid inversion of one amine into the inverted product takes place, and you will be having 50% of this and 50% of this. So it resembles now like a recipe mixture. The amine, although it has only one chiral center, but due to immediate flipping, what happens? Due to immediate flipping, amine flipping occurs, and the total amine exists as a 50% G and 50% L. So it now becomes like a recipe mixture which is non-resolvable. So that is why it is actually optically inactive in nature. So K equilibrium is equals to 1. So if you try to look at, okay, inverted, so retented is converting into inverted. So the retention to inversion complete equilibrium will be there. So K equilibrium will be is equal to concentration of inverted into divided by concentration of retented. The concentration of inverted and concentration of retented, they are going to be equal. So K equilibrium will be is equals to 1. Whenever the equilibrium constant is equals to 1, under that condition, what happens? Under that condition, we can say inverted and retented will be having the same concentration, so equal stability. So in that case, behaves as 50% D and 50% L forms or a semi mixture, so optically inactive. Understood this point or not, all of you? Whenever you have a single chiral carbon amine, in that single chiral carbon amine, you have 50% D and 50% L forms. That is, it is behaving as a recipe mixture, so it is going to be optically inactive in nature. It is going to be optically inactive in nature and cannot be separated. It cannot be separated, so non-resolvable. Separation of recipe mixture is nothing but resolution. But this recipe mixture cannot be separated. Why? Because the conversion of one form to other form is very fast. Barrier to conversion is low enough for conversion to occur at an observable rate at room temperature. So conversion is going to happen greatly. And you can say optical inactivity, optically inactive nature is due to flipping. Flipping, or also called as umbrella inversion. Umbrella inversion. We have discussed about all the cases. Chiral carbon 1, chiral carbon greater than 1 means plane of symmetry or center of symmetry. Chiral carbon 0 means allenes and biphenyls or alkylidyls. Yes or no? So conditions means second paired elements with one lone pair, like nitrogen, carbon, all those are second paired elements. Nitrogen has one lone pair, methyl, hydrogen, ethyl, carbon connected to three groups R1, R2, R3 and a lone pair. So these two are optically inactive in nature. Chiral nitrogen containing amines do not show optical isomerism. Reason, umbrella flipping or rapid umbrella inversion. Is that clear, students? Is that point clear to everyone or not?
Yes.
Yes, right. So this complete your part of isomerism. So just a second. So isomerism we have discussed about what all types. Any other isomerism we have left out? Tautomerism. As I have told you, the tautomerism I will be discussing in the GOC part. We'll start with GOC now. Okay, isomerism is actually two types, structural and stereo. Structural, chain or ring chain, position, functional group, metamerism, tautomerism. Stereo we have configurational and conformational. In the configurational you have geometrical and optical. In the geometrical we have cis trans, EZ and syn and anti. In the optical we have seen all about enantiomers, diastereomers, 3D projections, yes or no, Fisher projections. In the conformational we have discussed about the carbon-carbon rotation, free rotation, Newman projections, Swartz projections, potential energy diagrams at different cases. Yes or no? So this is very important part. So then comes to your GOC, general organic chemistry. So whatever the organic reactions we are going to study after this GOC, we are good to go with the organic reactions. GOC after, like what are the intermediates there, what type of bond cleavage occurs, what are electrophiles, what are nucleophiles, what are electronic effects, inductive effect, mesomeric effect, electronic effect, electromeric effect and hyperconjugation. So all these effects if we study, we can good to start with the reactions where all these effects are going to be useful. So understand this very carefully. So after this GOC, we'll be discussing reactions, different sets of reactions. After that reactions, we'll discuss about qualitative analysis and quantitative analysis and purification of organic compounds. Then we will go with hydrocarbons, alkyl halides, alcohol, phenol, ether, like that. It will be proceeding until the end of your organic 2. So right, let us start with GOC. Organic reaction. Organic reactions are the chemical reactions that are undergone by organic compounds in which the breaking of old bonds and formation of new covalent bonds take place. The old bonds are going to be broken and the new bonds are going to be formed. Any reaction, the generally bond cleavages happens, bond formations also happen. The general reaction is depicted as follows. Organic molecular substrate, it is treated with reagents. Substrate upon treated with reagent, it forms intermediate. That intermediate is going to be converted to respective products. Organic molecule, also called as substrate, upon treatment of the substrate with reagent, you get an intermediate. This intermediate will be converted to respective products. And you can also have byproducts. One product will be major and remaining all are said to be side products or byproducts. This is a general organic reaction. Okay. For any generalized reaction. Is that clear, students?
Yes.
Yes or no? Simple. For any generalized reaction, organic molecule treated with a reagent, we get an intermediate. That intermediate will be converting into products. That's it. Reaction mechanism. Reaction mechanism is a process of steps which gives complete information regarding all types of changes happening. The step-by-step process through which a reaction proceeds or a detailed study of reaction is known as reaction mechanism. Any organic reaction if you take, the detailed step-by-step analysis is nothing but mechanism. So if you have a substrate AB and if you have a reagent XY, substrate AB and reagent XY, they will react with each other to form an intermediate, and that intermediate will be unstable because it is a transition state where the repulsions are going to be slightly high, and that will lead to the formation of products AX and BY. Reaction, what is an organic reaction? So reactant is actually converting into product in a particular solvent. So A is an organic molecule, B is also organic molecule, or it can also be inorganic molecule, which is a reagent. Organic molecule, which is also called as substrate. So the reagent and substrate, they are going to be reacting now to form a product. What is substrate? Substrate is that reactant which supplies carbon to the new bond, and the other reactant is known as reagent. Like we have substrate and reagent, right? What is substrate? Substrate is that organic molecule which is providing carbon to the new bond. Reagent is what? Reagent is which is actually attacking the substrate. If both reactants apply carbon to the new bond, then choice is arbitrary. And in that case, molecule on which attention is focused, that is said to be substrate. Like we can have a reaction between two molecules where both the molecules are providing carbons to the formation of a new bond. In that case, which one is substrate, which one is reagent, that is not logical. Rather, we can say the molecule under which our focus is there. Like if I am studying about alcohols, then I'll take that alcohol molecule only as the substrate. Okay. Example, CH3Cl plus OH minus. CH3Cl plus OH minus will form CH3OH plus Cl minus. That means OH minus will be attacking this particular carbon. The carbon chlorine bond is leaves. So we get CH3OH and Cl minus. Which molecule is actually supplying carbon to the new bond? CH3Cl or not? So it is said to be substrate. And which is attacking the substrate? OH minus. So this is said to be reagent. And CH3OH is nothing but your product. Look at this species. Benzene plus CH3Cl in the presence of AlCl3 forms toluene. If you look at this, benzene is also providing carbon. CH3Cl is also providing a carbon to the new bond, carbon-carbon bond. So which is a substrate? Now we am taking, this is coming under the category of electrophilic substitution reactions of benzene. So I will take my substrate as benzene only and CH3Cl as a reagent. And product is nothing but your toluene. Toluene is nothing but your product. These are very basic definitions, like what is substrate means? Something which is actually providing the carbon to the new bond. If both substrate and reagents are providing carbon to the new bond, then the molecule under study, that is said to be substrate and the other is said to be reagent. If both the molecules are under study or under focus, then there is no meaning at all to call one is substrate and the other is reagent. Is that clear to everyone?
Yes.
Yes, right. Concepts to understand reaction mechanism. What are the concepts which we have and which we need to understand to have a command over the reaction mechanism? There are 4 points: bond cleavage, reagents, reaction intermediates, and electronic effects. So bond cleavages, what type of bond cleavages are there? Homolytic cleavage and heterolytic cleavage. Different reagents, electrophiles, nucleophiles. Reaction intermediates, carbocation, carbanion, free radical. Electronic effects. In the electronic effects, again the carbocation stabilities, carbanion stabilities, all those are going to be compared. Right? What type of bond cleavages are known, students? How many bond cleavages are known?
Heterolytic and homolytic.
Okay, when heterolytic cleavage occurs, Kanishka?
Electrons are unequally distributed in the compound.
Very good. So there are 2 types of bond cleavage: heterolytic fission and homolytic fission. Equal distribution of shared electrons, that generates free radicals. That means in any bond you will be having 2 electrons. If each atom has been given 1 electron, then that is said to be homolytic fission, right? This is said to be homolytic fission. Homolytic means equal distribution of shared electron. Heterolytic means unequal distribution of shared electrons. So AB, the two electrons which are present in the bond pair, one electron given to A, other electron given to B. So A dot plus B dot. Unequal distribution of shared electron, like if both the electrons have been given to B atom, generates A plus and B minus. Electronegativity of B is greater than A. If AB molecule is there, AB bond is there, and two electrons have been given to A atom, then in that case you get A minus and B plus. Electronegativity of A is greater than B. So in these two cases we have unequal distribution of shared electron pair. So homolytic fission, that will be resulting in the formation of free radical. Heterolytic fission, that will result in the formation of ions. Homolytic fission, when it is favored when the electronegative difference is low. Heterolytic fission is favored when the electronegative difference is more. Like CH bond, if you try to break this particular CH bond and give each carbon and hydrogen one electron, you will generate a free radical and a H dot radical. If a Z has more electronegativity when compared to carbon, in that case you will be generating both the electrons given to Z. You will generate what? The carbon will have a positive charge now, Z will have 2 electrons or Z minus. This is nothing but a carbocation. The carbocation is obtained when the carbon is connected to more electronegative atom and the heterolytic cleavage happened. And when the carbon is actually connected to less electronegative element and both the electrons given to carbon, then you will have what? If both the electrons have been given to carbon, then you will be having a carbon ion formed, and along with that carbon ion, Z plus is actually going to be obtained. Is that clear or not?
Yes, sir.
The species which attacks the reactive site of the substrate, that is said to be reagent. How many types of reagents are known to you? Types of reagents, there can be two types of reagents: electrophilic reagents or electrophiles, and nucleophilic reagents or nucleophiles. So what is electrophile? Electrophile is a reagent that takes away electron pair. It is nothing but electron loving. Yes or no? So electron seeking, and the reaction is said to be electrophilic. If a reagent which is accepting the electrons or taking away the electrons, then that particular species is said to be electrophile. Which has a tendency to take the electrons? Electron deficient species have a tendency to take the electrons. So electron deficient species which have a tendency to accept electron, that is said to be electrophiles. Can I say positively charged species with incomplete octet are electrophiles in nature? Like we have H plus ion. H plus is an electrophile. So first understand the concept. Electrophiles are those species which have a tendency to accept the electrons. So they are electron deficient in nature. So the positively charged species with a incomplete octet, they can accept the electrons. H plus is an electrophile or not? H plus is an electrophile. Na plus is an electrophile or not? Na plus can accept the electrons? Yes or no?
Yes, sir.
No, Na plus have complete octet. 1s2, 2s2, 2p6. Na plus has, although it is positively charged ion, it has complete octet. So it is not an electrophile, whereas H plus is an electrophile. Okay, not an electrophile. Na plus, it is not always positively charged species. Okay, H
Okay,
plus is
sir.
an electrophile. Okay. So we are going at all the cases. Positively charged with incomplete octet, H plus, NO plus, X plus, Cl plus, R plus, RC double bond of that carbon plus, pH N double bond N plus, NO2 plus. All Lewis acids are electrophiles. Na plus, K plus are not electrophiles. This is what I am saying. Why? Because they have already complete octet. Neutral molecules with incomplete valence shell like BF3, AlCl3, around boron, how many electrons are there? BF3 means
6 electrons.
6 electrons are there. So it is having only 6 electrons, whereas it can gain 2 more electrons to get octet electronic configuration. So BF3 has a tendency to accept 2 more electrons because it is electron deficient. So neutral molecules with incomplete octet, they can also behave as electrophiles. Positively charged with a incomplete octet. Positively charged with incomplete octet can behave as electrophiles. Positively charged with complete octet will not behave as electrophiles. Neutral molecules with incomplete valence shell, they can behave as electrophiles. We have different other categories also, like what are the other electrophiles? We'll discuss that in the next class. Fine. Thank you all, everyone.
Thank you.
Thank you.
Thank you, sir.
Thank you.